Welcome to Study Loop.
When the force of the pressure inside the cylinder is at the equilibrium with the weight of the piston, there is a specific value of this pressure that will fit the equation for this condition. But also we need to take into account that the atmospheric pressure is also acting on top of the piston. So we can draw it here like this. We have a cylinder, we have a piston, and this piston has some mass. It's not like completely massless. Now the force, there is a force of atmospheric pressure on the area of the piston. And there is also force of the weight of the piston. And inside we have a gas, it is under pressure, and this pressure is trying to pop out this piston, and this pressure also creates a force when we multiply the area of the piston with this pressure inside of the cylinder. So from Newton's laws, we can say that the pressure P, which is inside the cylinder, is going to be, has to equalize with two pressures. One pressure is the atmospheric pressure, that is P0 from the atmosphere. P is inside, plus what? The pressure of the weight, which is force of the weight over the area of the piston. So in that case, this equals to P0 plus, what is the force of the weight? Well, mass of the piston times the gravitational acceleration. And what is the area of the piston? When the piston is of circular shape, so we can say that it is P times R squared. Therefore, this is the final expression for the pressure under static conditions, when the piston is not moving and the pressure P equalizes the pressure P0 and the pressure coming from the force of weight. Next, for the part B of this problem, here we have also two forces. So there is an upward force, which is coming due to the pressure inside the cylinder, and we have the force of the weight of the piston, which is pulling the piston downwards. So to find the net force, we need first to subtract these forces. So we have F, which is due to pressure P inside the cylinder, and we have force, which is due to weight. Now we need to actually see what will we substitute for the force Fp. We know that it is some pressure times the area, but what pressure? So this pressure must have the atmospheric pressure counted out. So it must be the atmospheric pressure must be subtracted from it. Also, from the static condition, right here, we know that P will be equal to P0 plus mg over PR squared. But this is not the complete equation. The actual pressure that will go inside for this term would be the static condition pressure, so P0 mg over PR squared, times 1 minus y over h. This is the correction for the pressure, so that the pressure is normalized. And this is going to be minus P0 because we don't want the contribution of the atmospheric pressure. Otherwise, we will have to count in the force of the atmospheric pressure on the subtracting side. So this will be multiplied with the area of circular shape element, which is PR squared, and then minus mg, which is the force of the weight. So here we can rearrange this. We can completely change the way that algebraically this looks, and also we can see that when P0 gets multiplied by 1 and then subtracted by P0, it will be cancelled out. In similar fashion, every other term will find its place, and after we complete algebraic transformations, we obtain that the final expression for the net force is that F net equals minus y over h P0 times pi times r squared plus mg. So this is what we obtained when we multiplied everything out here, canceled everything that can be cancelled out, and then simply took the common multiplicator outside of the brackets. And this is for the part B of the problem. Now for the part C of the problem, we have an oscillating case where the piston oscillates as a spring due to a specific set of conditions. So first we need to start, since we need to find the frequency of the oscillation and compare this frequency with the harmonic oscillations or harmonic oscillator, simple harmonic oscillator, we know that frequency in general is the angular velocity all over 2p. And so here we can, and first we need to actually evaluate the angular velocity. So for this kind, for this piston, the angular velocity, the square of angular velocity will be equal to all of the forces over h and then over m. So this will be P0 times pi times r squared plus mg over h, and then all of this is going over m. And to make some algebraic transformations here, to make this look better, it is going to be g over h times 1 plus P0 pi r squared over mg. Since this is going to be the square of the omega of the angular velocity, then the frequency will be 1 over 2 pi square root and the square root of the whole term here. So g over h 1 plus P0 pi r squared over mg. And this can be further represented that f is 1 over 2 pi, then only g over h under the square root, and this term will be P0 pi r squared over mg raised to the power of 1/2. So these oscillations are not like simple harmonic oscillations. Why? Well, only this part here looks like simple harmonic oscillation frequency, and we have the whole square root function here in product with this part. So no, the oscillations will not be like simple harmonic oscillations, and the frequency function is much more complicated. And by this, we have completed the whole problem. I hope you find it helpful.